Okay, so yeah, my name's Ryan Judd, and I work within the drainage operations team in Natural Resources South East, and we work on behalf of the South Eastern Water Conservation and Drainage Board. So today I hope that my presentation will demonstrate how we're using data collection and some science to improve the operations of regulators within the South East Drainage Network. And today I'm going to use the example of Magarey Lane regulator, which is in Drain M, for those of you that know the network. So a bit of background on the drainage network. We've got a map here, so you can see that the South East Drainage Network has developed into a huge system that covers most of the South East. So the South East Water Conservation and Drainage Board is responsible for managing all of these drains, and there's over 2,500 kilometres of drains, and then there's connected water courses and wetlands that need to be managed as well. So this is the Magarey Lane regulator that's going to be used as the example today. It's quite a big structure. So since it was constructed in 1981, there's been quite a bit of debate about how this regulator should be operated and the different effects that operations are having on the local water table and land productivity for the surrounding landholders. So the main debate comes back to the topography of landholders' land. So the ones within close proximity to the regulator, they have high lying land, and they prefer the regulator to hold water up during most times of the year, because they believe that that Drain M is too efficient and it's actually lowering the water table. And then in contrast to that, the landholders upstream, they have some lower lying land, and they prefer for the water basically to be held as low as possible during winter, and then built back up once you get back to summer. But there's also some environmental aspects that need to be considered as well, because we can't just let all this water go, because it's been identified as a refuge site for pygmy perch. So that has to be considered as well. So basically the idea of the investigation was to work out the actual effect that the regulator was having on the local water table, and then use these results to produce an operational procedure that hopefully benefits all aspects as equally as possible. So you can see here this red dashed line. This is the monitoring transact that was established. This was just done using existing observation wells and private wells, so that was good. And you can see the red dot there, that's the regulator in the drain. So using the data collected from this monitoring transact, and there's also a monitoring station set up at the regulator that's recording water level. It does 5-minute readings within the drain. So if you just look at this plot, the top line, just got purpley colour, that's the topography. So if you imagine that this transact here has been cut through the earth, and we're looking into the earth and the drain, that's what the plot's showing. And so you can see the big dip in the middle there, that's Drain M, and the yellow dots are the locations of the observation and private wells. And then the light blue line in the middle there, that's the surface water level within the drain, and then the dark blue line is the water table. So common practice within the drainage network is to, leading into winter, at the beginning of winter, regulators will begin to be opened to get surface water moving, and allow some storage for the incoming rainfall and winter flows. And this is just to mitigate inundation of landholders. So that's what this graph is showing. So this top graph is before the regulator was open, and then the bottom graph was 20 days after the regulator was opened. And so you can see that obviously the surface water level in the drain has dropped And this has impacted the local water table, so it's had a noticeable drawdown effect within about 300 metres either side of the drain, and then a minimal drawdown effect up to 1.5 kilometres either side of the drain. I can't show you all the transects because there's quite a few of them, but I'll show you this one at the beginning of winter when it was opened, and then this one is in spring, so following the winter when the regulator was begun to be closed back up. So like at the start of winter, in spring, common practice is that regulators begin to be incrementally shut to capture the tail end of the winter flows and to retain water within the landscape, and also to try prevent any over drainage of groundwater resources as well. So as you can see, again, the top one is before the regulator was closed, and then the bottom graph here is after the regulator was closed. So you can see that the surface water level in the drain has increased quite a bit, and it's actually surpassed the water table, whereas before it was below it. And this has produced a small groundwater mounding effect within close proximity to Drone M. So the next step of the investigation was to produce a time series of contour maps to look at the influence that the regulator and the surface water level in the drain is having on the local groundwater system, and use this to give a bit of a bigger picture of the area. And so this is in winter. Again, I can't show you all the maps, but this one's during winter, so you can see that there is a bit of a groundwater mound effect around the regulator. So this one was after the regulator was shut, so you can see that the groundwater mounding it's increased quite a bit, the level of the groundwater table, and it's really within real close proximity to that regulator, and it's affecting about 1.5 kilometres to the north, but then about 3 kilometres to the south. And this could be because the Simon drain, which you can see there, has a bit of a backwater effect, or it could be different lithology on either side of the drain. This is providing a good outcome for landholders within the area, because it's showing that it is helping hold up the groundwater within a small area, and you can see there's a centre pivot there, so it means that if we're increasing that shallow water table, then landholders might not have to irrigate, or they might have to irrigate as early. And it also can improve the efficiency, because they might not need to use as much water when they are irrigating. But it's important to note that this groundwater mounding effect doesn't really, it's not lasting forever. So this is in January, so this last one's in November. So you can see by the time it gets to January, the configuration of the contour lines has reverted back to a similar configuration that we saw at the beginning of winter. So the landholders are receiving their best benefit from the regulator for about 3 to 4 months. So this is the outcome. So following this data collection and then some interpretation of the influence that the regulator and surface water has on the local water table, I was able to produce a operational guideline for the regulator, which this is a good outcome, because it means that instead of just someone going out and being like, oh, it's a bit, the landholders are saying it's a bit wet around, they want the regulator opened a bit, and go out and open the regulator. There's set target levels for each season, and these have been shown to benefiting landholders, and the levels that are tried to benefit the landholders, all the surrounding landholders around there equally, but also the environment as well. And it's also been a good outcome, because it means that, so instead of just one person knowing how the regulator works, any of our staff can take this operational guideline and go out and operate the regulator if needed to the correct level. And this comes in handy because we have 187 regulators across the network to help us achieve different objectives, and so this comes in handy. And it's also a benefit to the landholders, because they've got to have a say and see what has gone into deciding these target levels. and it's helped build that relationship there. And it's also, it allows them to be able to check each time of year what the level should be, and then what factors we are going to consider to alter these levels if needed, such as extreme rain events and releases of water from upstream regulators. Yeah, so that's it. Thanks.